the universe from its fiery origins to the sprawling cosmic web we observe today. But now, the Webb telescope has caught a glimpse of something that defies everything we thought we understood about the cosmos. It's seen the first object beyond the Dark Ages, a period when the universe was shrouded in mystery. And what it found has left scientists around the world stunned. This isn't just a discovery, it's a revelation that could upend our entire understanding of the universe's earliest moments. So what exactly did the Webb telescope see, and why is it causing such a stir? Let's dive into this cosmic enigma and explore what it means for the future of science. Our universe, as we understand it, began roughly 13.8 billion years ago with the Big Bang, an explosive event that set everything in motion. In its infancy, the universe was a hot, dense soup of particles rapidly expanding and cooling. For a time, it entered a phase known as the Dark Ages, a period lasting hundreds of millions of years where the cosmos was cloaked in dense clouds of neutral hydrogen gas. This gas was so thick that light couldn't travel far, rendering the universe opaque. No stars, no galaxies, just an endless sea of gas and darkness. According to our models, the first stars and galaxies didn't form until the end of this era, when the universe began to ionize, allowing light to shine through. But here's where things get strange. For decades, astronomers have detected faint glimmers of light piercing through this cosmic fog, hints of something luminous existing where nothing should. These mysterious signals have puzzled scientists, as our telescopes, even the mighty Hubble, couldn't peer deep enough to unravel their origins. Enter the James Webb Space Telescope, humanity's most advanced eye on the cosmos, designed to look further back in time than ever before. The Webb telescope, with its massive 6.5-meter mirror and infrared capabilities, was built to probe the universe's earliest chapters. Unlike visible light, infrared can penetrate the dense clouds of the Dark Ages, allowing us to see objects that were previously hidden. And what it's found is nothing short of astonishing. In a recent observation, the telescope captured an image of a luminous object, a galactic structure shining brightly in the early universe, at a time when, according to our models, no such structure should exist. This object, located at a redshift of approximately 15, places it roughly 13.5 billion light-years away, meaning we're seeing it as it was just 300 million years after the Big Bang. To put that in perspective, this object existed during the heart of the Dark Ages, a time when the universe was supposedly too young and too opaque to host such bright, complex structures. This discovery is forcing astronomers to question the very timeline of cosmic evolution. What makes this object so extraordinary? For one, it's not just a single star or a faint protogalaxy. It's a massive, highly luminous structure, potentially a galaxy or a cluster of stars, radiating intense light in the form of Lyman alpha emissions. These emissions are specific wavelengths of ultraviolet light produced by young, hot stars as their energy excites hydrogen atoms. In the early universe, such emissions should have been absorbed by the dense hydrogen clouds of the Dark Ages, making them invisible to us. Yet the Webb telescope has detected these emissions loud and clear, suggesting that something was clearing paths through the cosmic fog, allowing light to escape. Scientists now believe that this object was surrounded by bubbles of ionized hydrogen, regions where the gas had been energized by intense stellar activity, creating transparent channels for the Lyman alpha light to travel through. This implies that star formation was happening on a scale and at a time we didn't think possible. But the surprises don't stop there. The object's sheer brightness and complexity suggest it's not a lone outlier, but part of a larger cosmic phenomenon. The Webb telescope's deep field images have revealed other similar structures, some at even higher redshifts, pushing the boundaries of what we thought was possible. One such object, tentatively named Jade's GSZ-16, is among the most distant ever observed, existing just 250 million years after the Big Bang. Its redshift of 16 places it firmly beyond the Dark Ages, challenging the idea that galaxies only began forming at the end of this period. These structures are massive, hosting billions of stars. Some even show signs of harboring supermassive black holes at their centers, objects that, according to our current models, should take billions of years to grow to such sizes. The discovery of a supermassive black hole in a galaxy just 400 million years after the Big Bang has left astronomers reeling. How could such a massive object form so quickly? The death of the first stars or the merger of smaller black holes simply doesn't account for the size and scale of these cosmic giants. These findings are sparking intense debate among cosmologists. Our standard model of cosmology, known as the Lambda Cold Dark Matter (CDM) model, has been remarkably successful in explaining the universe's large-scale structure, from the distribution of galaxies to the cosmic microwave background. But these new observations are pushing its limits. If galaxies and black holes were forming this early, It suggests that the universe's timeline may be off. One possibility is that the universe is older than we thought, perhaps significantly so. If the Big Bang occurred earlier than 13.8 billion years ago, it could give these massive structures more time to form. But this idea raises its own problems, as it would require rethinking the cosmic microwave background, the expansion rate of the universe, and a host of other measurements that align with the current age estimate. Another possibility is that something accelerated galaxy formation in the early universe. Some scientists propose that the conditions after the Big Bang were far more dynamic than we realized, with intense bursts of star formation triggered by mergers and interactions between proto-galaxies. These mergers could have compressed gas clouds, sparking the rapid birth of stars and black holes. The Webb telescope's images show evidence of such interactions, with distorted galactic shapes and bright bursts of star formation. These early galaxies appear to be far more chaotic and active than their modern counterparts, suggesting a universe that was anything but calm in its youth. But there's a more radical hypothesis gaining traction, one that challenges the very foundations of cosmology. It's called conformal cyclic cosmology, CCC, a theory championed by Nobel laureate Sir Roger Penrose. In this model, our universe is just one in a series of cycles or eons, each beginning with a Big Bang and ending with the evaporation of black holes. According to Penrose, the energy released from these evaporating black holes in a previous eon could seed the rapid formation of galaxies and black holes in the next. This could explain why we're seeing such massive structures so early in our universe's history. They may carry the imprint of a cosmos that came before. While this idea is speculative, the Webb telescope's discoveries are lending it new credibility, as they suggest that our universe's early evolution was far more complex than a simple linear progression from the Big Bang. The implications of these findings are profound. If galaxies existed beyond the Dark Ages, it means that star formation began far earlier than we thought, potentially reshaping our understanding of cosmic evolution. The presence of supermassive black holes at such early times challenges our models of how these objects form and grow. Some scientists are even questioning whether the Big Bang was truly the beginning of the universe, or merely a transition point in an eternal cosmos. The idea of an infinite universe, with no definite start or end, is gaining traction as we grapple with the sheer scale of what Webb is revealing. The Webb telescope's near-infrared camera, NIR-CAM, and near-infrared spectrograph, NIR-SPEC, have been instrumental in these discoveries. By analyzing the light from these distant objects, astronomers can measure their redshift, which tells us how far away they are and how long ago their light was emitted. The higher the redshift, the further back in time we're looking. The objects Webb has found, with redshifts ranging from 15 to 16, are among the most distant ever confirmed. Spectroscopic observations, which break down the light into its component wavelengths, have revealed the presence of heavy elements like oxygen and carbon in these early galaxies, elements that can only be produced inside stars. This suggests that these galaxies had already gone through multiple cycles of star formation and death, producing the heavy elements we see today. This is astonishing, as it implies that the universe was already chemically complex just a few 100 million years after the Big Bang. The discovery of Lyman alpha emissions is particularly telling. These emissions are produced when electrons in hydrogen atoms drop from a higher energy state to a lower one, releasing ultraviolet light. In the early universe, this light should have been scattered and absorbed by the dense neutral hydrogen gas of the Dark Ages. But the Webb telescope's observations show that these emissions are escaping, thanks to bubbles of ionized gas carved out by intense stellar activity. These bubbles act like windows, allowing light to travel unimpeded across vast distances. This phenomenon, known as reionization, was thought to have occurred later in the universe's history, around 500 million to 1 billion years after the Big Bang. But Webb's data suggests that reionization may have started much earlier, driven by these unexpectedly massive and luminous galaxies. The supermassive black holes are another puzzle. In modern galaxies, these objects sit at the centers of most large galaxies, including our own Milky Way. They grow over billions of years by accreting gas and merging with other black holes. But the black holes Webb has found, like the one in the galaxy GNZ11, are already enormous, with masses millions or even billions of times that of the Sun, just 400 million years after the Big Bang. This is a serious problem for our models, as there simply wasn't enough time for these objects to grow through conventional means. One theory is that these black holes formed directly from the collapse of massive gas clouds, bypassing the slow process of accretion. Another possibility is that they were seeded by the remnants of a previous universe, as proposed by Penrose's cyclic model. Whatever the explanation, these black holes are forcing us to rethink the physics of the early universe. The Webb telescope's discoveries are also shedding light on the process of galaxy formation itself. Modern galaxies like the Milky Way are highly structured, with spiral arms, bulges, and disks. But the galaxy's web is seeing are chaotic, with irregular shapes and intense bursts of star formation. These early galaxies are often engaged in violent mergers, which compress gas and trigger the rapid birth of stars. This frenzy of activity could explain why these galaxies are so luminous, and why they're producing so much Lyman alpha emission. The mergers also provide a clue to the rapid growth of supermassive black holes, as the collisions could funnel vast amounts of gas toward the galactic centers, feeding the black holes and allowing them to grow at an accelerated pace. So what does all this mean for our understanding of the universe? For one, it suggests that the early universe was far more active and compact than we thought. Galaxies were forming, merging, and producing stars and black holes at a time when the cosmos was supposed to be a quiet, dark place. This challenges the standard timeline of cosmic evolution and raises the possibility that our models are incomplete. If the universe is older than we thought, it could resolve some of these discrepancies, but it would require rethinking many of our fundamental assumptions. Alternatively, the universe may have undergone a phase of accelerated evolution driven by mechanisms we don't yet understand. The conformal cyclic cosmology model offers a tantalizing explanation, suggesting that our universe is part of a larger cycle, with echoes of a previous cosmos influencing its early development. The Webb telescope's discoveries are also breaking records left and right. In just a few years of operation, it has identified the most distant galaxy, the most distant black hole, the most distant protocluster of galaxies, and even the most distant quasar. Each of these findings pushes the boundaries of what we thought was possible, forcing us to confront the limitations of our current theories. The telescope's ability to peer into the infrared has opened a new window on the universe, revealing objects and phenomena that were previously invisible. It's no exaggeration to say that the history of astronomy may soon be divided into before Webb and after Webb, as its discoveries are reshaping our understanding of the cosmos in profound ways. But perhaps the most exciting aspect of these findings is what they suggest about the future. If the Webb telescope continues to uncover objects beyond the Dark Ages, it could provide the evidence needed to confirm or refute some of the boldest ideas in cosmology. Spectroscopic observations of these high redshift galaxies are still ongoing, and if they confirm the predicted distances, they could shatter the foundations of our current models. The idea of an infinite universe with no definite beginning or end is no longer just a philosophical musing. It's a hypothesis that's gaining traction as we uncover more evidence of an ancient, complex cosmos.